how did we get to this point? How do we get to this point with a significantly fragmented industrial base, massively consolidated OEMs, really complicated problems, and now you've got geopolitical issues that are going to potentially bring an enormous amount of work back to the United States, but people are starting to raise the flag and saying, wait a second, our supply chains aren't resilient enough. And so,
As
I,
it
yeah,
seems like everyone agrees it's really broken, and everyone kind of feels like they're not sure where to start. When we look at just from the standpoint of our suppliers, right, or our customers, which are typically suppliers into these ecosystems, like take suppliers into aerospace and defense, right? Um, they've got real challenges in just doing their jobs like on a daily basis, right? And they get information that is drawings, PDF drawings, 2D drawings, sometimes drawings with a 3D model in it, sometimes a bunch of 3D models. And they've got to figure out how to make use of that information. And often that information isn't in a way that is easy to use. It's just like,
yeah.
it's just given to them with the expectation they're going to be able to figure it out. And I think maybe if you wouldn't mind, like, why is CAD even a thing? Like, how did this come about?
Yeah, I mean, I wish I was a part of the industry when it was evolving. So I'll give you the layperson's story in terms of background, but I look at the history of AutoCAD, 2D drawings, engineering drawings, going back to like the 1970s with CATIA, AutoCAD coming in the early 80s. And then really, I think the breakthrough moment was a local Boston company, PTC, with Pro Engineer. And PTC changed the game with 3D modeling. Like they made a solution that was vastly more powerful and easier to use than anything else out there. And I think that kicked off a little bit of a chain reaction. All right. So you imagine an engineer trying to design and draw something in a 2D world, right? So that's incredibly difficult to achieve the levels of complexity and the ability to communicate something that is 3D in 2D. It's rife with problems. So design was massively constrained by the technology. Well, then Pro Engineer came on, and these CAD systems started getting better and gave birth to arguably the most prolific CAD system in the world, which is SolidWorks. Again, another Boston-based company or Massachusetts-based company. Um, and it totally started to change the paradigm. Now design was getting a lot easier. So design engineers could go in, they could interact in 3D, they could very quickly prototype out the shapes and designs and massively large assemblies that they needed to produce. They could see how things could fit together. Then you started to get companies like ANSYS that allowed you to understand how something would perform with a certain type of metal, with a certain computational fluid dynamics and finite element analysis. And all of these computer modeling solutions have now allowed us to operate in, what, ones and zeros instead of having to go and effectively build a model the very first time you're trying to design something. So I think it's an amazing evolution, but I think that kind of that moment, that big bang moment, kicked off a ripple effect that I don't think anybody really saw happening. And I can't say what the CAD executives were thinking, but a lot of folks were, I assume they're sitting in the room and they're like, this is great. We'll create proprietary file formats. We'll make it seat-based licenses. And then our sales team will literally go hammer every company in the world and force them to use our tools.
Yeah, you
And that,
had,
yeah,
and it was a bit of an arms race, right? I think it's kind of hard to overstate how important this was, though. So let's just like paint the picture of the 80s in designing an airplane, right? So computers by then were relatively advanced, at least compared to no computers at all. And you would design every individual component of an aircraft in isolation, just taking an aircraft as an example, right? Because this is one of the places where this really pushed. You then had to go build an aircraft from scratch to make sure every single piece fit together, right?
yeah,
The the amount of waste and time to develop an aircraft like, say, the 767, right, that was developed ahead of the 777 or 757, right? And those things are still flying, but frankly, the the speed with which, just the speed alone, if you could design an aircraft all in one system without having to make a model of it, was enormous for transforming industries, right? Not just aerospace and defense. You could imagine heavy machinery being exactly the same way, right? Like a John Deere harvester without having to do the same thing.
And so let's start to hit some bullet points, right? So speed, everything got faster. I would argue it also got more complicated because now CAD enabled degrees of freedom that engineers never really thought about. And it was easy to model in 3D, but then when it got into a manufacturing environment, people said, wait a second, like you can't drill a hole like that, or you can't produce a face like that. And manufacturing hardware has come massively in the last 2 decades, but it lagged software by a quarter of a century, arguably. I mean, 5-axis machining really, really only started to take off in like 2000s, early 2000s into 2010 and so forth. Like when we first started this company, the vast majority of the companies we were talking to were using 3-axis machines. It was crazy
Well,
to think
because you
about.
don't, because most, go back to your 80s here, right? So if you had to, when you were designing, take just the same example, you're designing an aircraft. So you had to create an actual model of what you were doing in real life scale, full scale model. So if anything wasn't going to fit together or made no sense to manufacture, you were going to know
That's
because you had to
exactly
actually
right.
do it.
And that is such a paradigm shift from the way products were designed to the way products are designed now. And I think that that's an enormous ripple through the supply chain. So it went from physically knowing that you could produce every single component the way it was designed and that it all fit together to having a theoretical model. And I'm sure what was the first plane that was designed with CAD entirely?
So the first plane that was ever done was the 777, the Boeing 777. They used CATIA in Dassault systems. And you can imagine, and it was actually an unbelievable accomplishment. The entire thing fit together without ever building a model.
I mean, so that totally transformed the entire world and how things get designed and how things get modeled and the efficiency upstream in the supply chain. And you know what the saying, right? It all shit rolls downhill. So now you're in a situation where you either need every single one of your vendors to be playing in CATIA or in Pro Engineer or in SolidWorks in order to access these proprietary files, or you basically have to revert to the lowest common denominator, which is a PDF drawing. Now, that became the path primarily because CAD and CAM were separate, just different software solutions, and the model did not have any amplifying information. So you can only model a CAD model to specific tolerances. Like you cannot go past a certain tolerance level in a CAD model. At a certain point, the I don't know, like the pixelation of the model, it needs to be defined with amplifying callouts that say this is -0 plus half a thou. And I think that made it really easy for the supply chain to just say, don't send me these stupid models. I don't want to pay for a seat of CATIA. I have Mastercam from CNC Software. I'm going to use my Mastercam license, or I'm going to use my Hypermill, or I'm going to use my Solid Cam. I mean, the evolution of CAM was happening on the side as well. And there was no synergy to basically loading the model in the early days. Now I can take a CAD model, load it into my CAM system, and I'm getting off to the races a little bit faster. But in the early days, it was like, don't send me the CAD. Just send me the PDF drawing. It has all the information I need. And everyone reverted back to the lowest common denominator.
Because the CAD alone isn't enough,
That's
right? To,
exactly
to your point, because it doesn't have And even now, you could argue with MBD files now that the PMI is in the CAD file, which by the way, if we ever saw them, which pretty much don't ever see them, but if you had them, in theory, the file format can now support a lot, if not all of the manufacturing information. But you go back 20, 30 years, the PDF was required no matter what, right? And so sure, the CAD file, they may send the CAD file, but unless you were if you're thinking about the supply chains, right? Unless you're a relatively sophisticated supplier, and typically sophistication is going to come with size, because with size comes budget comes engineers, ability to actually make use of some of the more advanced CAD systems, or even just some of the better CAM systems, right? Like just kind of by definition, if you're larger, you're going to have better tools. And so you had to send the PDF no matter what, the 2D drawing, then it became a question of, okay, so when we're putting together these technical data packages to send down to our supply chain, what are we going to include? And and these typically these products that you're developing have 10,000 components to them, 20,000 components. So if you multiply that by the number of pieces of information you have to send in a single technical data package, you start getting into a multiplier effect of the number of things you have to have. I mean, if you look at a BOM structure on just a basic assembly that goes into an airplane, you'd be talking about thousands of files for just a single assembly, not the whole airplane.
Yeah.
So it just became a question of how do we even pull this off? So you just send the engineering drawings, because the engineering drawings, have everything you need.
And the files were enormous.
Enormous.
People forget email was not really a thing. I was still when I was working at Naval Sea Systems Command and we were buying missiles, we were still getting our proposals on CDs because of how enormous they were. There was not a secure way to go and send gigabyte size files.
And remember that a lot of the stuff is controlled, right? So even if it's just a standard airliner, commercial airliner in the US, you're going to have stuff that people are going to care about export control. And if you're thinking about anything defense oriented, then almost everything is going to be controlled. And email is not secure, right? There are forms of communication that are quasi email or they're secured email, but those are modern, right? Yeah. Traditional email is not secure, so you couldn't use it that way. And so you didn't have, FTPs, like you started to get into kind of the gray area of technology about how you're going to even send this information. DVDs could do 2.4 gigabytes. A CD was 700 megabytes, right? But if you go back to kind of when this stuff was developing, a single computer alone, like a personal computer, I have a hard drive of 500 megabytes, right? You can't fit anything on that. And so what ended up happening was you take the design CAD files that incorporated everything, the entire airplane, many, many gigabytes of information. You had to find a way to shrink that, right? Yep. And so what they would do is they would compress it, not like in computer terms, but just in more general like frameworks. Like, okay, what information can we remove from this that will keep the basics? And typically what they would remove is all the details. And so you would have this file that would have whatever the exterior of whatever the part is that you're making, just so you know that the exterior dimensions, right? Just so you know that it would fit, right? It was, and like Boeing calls this a lightweight gravity or a low weight gravity file, kind of TBD on which one of those is the right one. But that ended up becoming kind of the standard way to approach this in the industry, not necessarily those terms, but that kind of idea, which is, wow, way too much information in these CAD files. The CAD files are huge. Our computers aren't nearly powerful enough to handle them unless you have a mainframe sitting somewhere in Boeing's case, like in Seattle, Everett, Washington. These are huge mainframe files. How do we get this in a way that can be sent down the supply chain?
And that was the creation of STEP as well, right? The STEP file format was officially released in 1994. And that was really focused on giving a interoperable model that you could, because you needed to be able to go from CAD to CAM with something. And that interoperability, you needed a common format for it, but it dropped things like tolerances, material properties, any amplifying notes. It just did not, that did not cross compute. So you really lost a lot. There was no way you could stay in CAD. So going back, right? Design got faster, parts got more complicated, assemblies got larger. Manufacturing knowledge in the OEMs started to decline. On the other side of the fence, you have our customers today, manufacturers, and the timing is really interesting because when you think about a lot of the folks we talk to with 30 years of experience, this is like 95 is when they were getting their careers going. Now you step back and it's like, well, of course, they had to get really good at reading drawings, understanding what's going on, understanding what it would take to produce a very complicated part off of a drawing. It was trial by fire. Like you had to get good at it.
You had to try to interpret design intent.
Yeah. So all of that tribal knowledge has been built up over the last few decades as these kind of very slight evolutions in the way we communicate are happening. So I think the first real whack at trying to solve this problem and get everyone playing on the same field was model-based definition files. Back in 2003, I think, is when they released the model-based definition file standard. And they said, hey, this is ludicrous. We have a drawing and we have a model. And when we have both of those things, it creates enormous problems for everyone involved. Change management is really difficult. Now we need to go rev something. We have to worry about, do we change the drawing? Do we change the model? It's really difficult to communicate downstream in the supply chain. That's really difficult. What's the source of truth? What's the contract based on? And so the industry got together and said, okay, well, this would be amazing if we could embed all of the key information inside of the CAD model. Mind you, computers are getting more powerful. Things are getting faster. The internet is coming full fruition now, really kicking full steam. And people are saying, okay, well, we gotta evolve. But the problem is you have 50 years of legacy data that has not been designed using any type of model-based definition files. And you have an entire supply chain that still cannot open a model-based definition file. So whereas the industry saw this as a way to raise the fidelity of information for the entire supply chain, a lot of the CAD producers saw this as another way for them to drive their business model, which is selling seats. And so just like anything else, they figured out ways to embed unique information in their MBD files that did not mesh with a common file format. So now fast forward, I think STEP got updated, 2014 was the first STEP 242 file format. So now we're like, okay, well, we have a STEP file that contains none of the amplifying information. And you know how governing bodies work. 11 years later, they finally come to an agreement on what a common file format should look like for model-based definitions. So now we've got model-based definition file, but no engineer knows how to use MBD files in the CAD systems. Even to this day, they don't know how to do it.
And there's a practical reality too to this, which is that there's a question of where do you start? Because, okay, so great. Now we have a file format. Now we've got, assume that the tools all support it, which they did relatively quickly. But one, training, as you mentioned, there's training and there's change management at any OEM or ODM. From there, you have a change management everywhere else that has to receive this file. But frankly, the problem is bigger and upstream, because the majority, if you look at what our customers make, you look at what most of the machine shops, fabricators in the US and abroad are making, it's not new stuff, right? Yes, there are some things that are new.
The old stuff.
Exactly, right? There's plenty of stuff where a SpaceX or an Anduril or a Blue Origin are making, Firefly Space, right? Like, name any of the space exploration companies, any of the modern military companies. Yes, absolutely. Our customers support that stuff all day long. That stuff tends to be relatively well documented compared to everything else. but
Yeah.
the vast majority of the parts that are being made are sustainment. It's stuff that is already there.
Yeah. I mean, it's Airbus and Boeing is a great example. Like
Totally.
Boeing has 100 years of history that they have to deal with, and Airbus does not. And so when you think about their supply chains and the history there, they've really got to be careful. It's just,
You know,
yeah,
so do you know when the first Chinook was developed?
no.
You know, when it took the first flight, you know, the Chinook, the 47, CH-47.
Yep.
The first flight was in 1961. You know what the current Chinook is? It's the K variant, the CH-53K, or I guess that's a 53. They've developed it further. But that means you've got parts that were originally designed, or airframes that were originally designed in the 50s.
Yeah.
And so you're looking at those customers, you're looking at companies like Eaton, right, that sit on several million parts, that the majority of their business was through acquisition, right? You can say all day long that they're an Irish company, but they're not. Most of their stuff is through acquisition, and it's through it's legacy parts and assemblies and sub-assemblies. That stuff was designed on via hand drawing.
Yeah.
So you have to then, if you're going to support model-based definition files, you have to go in and actually create them.
Yep.
And if you want to go create them, that's a massive undertaking, because a model-based definition file isn't just automatically generated. And you're going off of a hand-drawn part that is the actual, as you've said, it's the contract. Whether or not it actually has a signature on it doesn't matter. It's kind of like, you know, it's like case law and law, where it's like there's been precedent to the fact that this is now the contract. This is the thing we go off of. And so you have to then say, okay, well, what if there's a mistake? What happens? Who's liable? Right? And so it would be a massive undertaking. So very few companies have done it, except for NPI, except for new part introduction, new product introduction.
So we have speed, innovation cycles are getting faster, parts are getting more complicated. We have legacy data that is kind of like, we'll call it organizational debt, for lack of a term, design debt, tech debt. And now you have fairly slow iterations throughout the supply chain, because we're falling back to this common file format of a PDF, because Adobe had the foresight to make it so that anybody, I mean, my first Windows computer was, I think, a Dell, and you could open Adobe PDFs. Like, they created a common file format that was lightweight that every person could open, right? But now you have this lag that's a result of these PDF drawings, and you pair that lag with the fact that the OEMs are no longer building the first iteration themselves. And all of a sudden now you have a problem that needs to get solved, because I've got a lot of speed here and I've got a lot of slowness here. And I can just picture engineers saying, why can't we just theoretically manufacture these and run some kind of a DFM analysis on it that also then shuts up the supply chain people who are whining about how expensive all these parts are that we're designing, and we're just trying to make planes faster and lighter, so they just need to get on board. But all of a sudden, come 2003, a priori. So a priori comes onto the scene, right? Product cost management, design for manufacturability. And now I can take a 3D model, and even though my supply chain can't interact with that, I can still feed that 3D model into a priori, and I can get rough theoretical, could you machine this in this part of the world? And like, what do the rates look like? And I think that solution really bridged. It was like a massive crutch for solving a supply chain inefficiency problem for really a decade and a half, maybe a little bit longer.
Well, and so what you had happen was, because you had this software and because you had this divergence between the design engineer and actually having to make the aircraft, right? Where there was a feedback loop, because there was a giant hangar where someone was putting stuff together that they would have walked back over to the engineers, the design engineers, said, guys,
this doesn't fit.
What you designed doesn't fit. We got to do something different. And so that was a natural feedback loop, right? And there was also more vertical integration at that point. Just more of the aircraft was being built by the company. When you shift that to this virtualized world now, and you have this proliferation of supply chain where you're kind of, for a lot of reasons, corporatism, but also just specialization, you had these supply chains start to fragment. You had to create, they had to find a way to get that feedback loop going again, right? And a priori is an amazing tool for that. But you had this kind of the emergence of the manufacturing engineer at the OEM.
Yep.
That the idea was, well, you got the design engineer who doesn't really think about how something should be made. And you then have the manufacturing engineer whose goal is to say, how do we think this is going to be made? And that was really the primary user of a priori, right? And that's how you had that feedback loop. The problem you had was actually a practical problem with that. And we see this all day long with our customer base, is a priori is amazing for telling you how something could be made and all of the theoretical outputs to it. But what happens when you actually go to have it be made?
Yeah.
Supply base may or may not actually do what they were thinking. So you have all this expectation built on a target cost or a designed cost that or a simulated cost that you're getting through your manufacturing engineering organization and your a priori licenses. And by the way, all this stuff is amazing. It just fails the practicality test all the time.
And it is a really hard problem. Software is hard. Like, we know this.
Really hard.
Software is really, really hard. It is even harder to maintain a common understanding of an industry that is evolving at light speed. I would say over the last 2 decades, manufacturing technology has exploded in capabilities. The convergence of hardware and software and compute power and the ability to drive machines in unique ways and design tools, like the ability to design more complex parts, also allowed for the design of more complex fixturing and more complex tooling. So you started to go from a world that was fairly well defined in 2003, like pretty well defined. Every manufacturer is going to have 3-axis bridge ports. They're going to have a Haas machine. It was a well-known landscape, to something that is just a complete Frankenstein. And at the same time, now you end up with manufacturers that are more than willing to bend the rules in order to get jobs done. Like, we've had customers that tell us crazy stories that are not advisable, but like taking the door off the machine to fit a part inside of the machine. Like, there are no rules that govern that.
One of the crazy things to me is when you look at the innovation that's going on in both the production itself, which is a little bit of what you were just touching on, which is things like fixturing, using tabs, right? Things that we're completely innovating in how you could make something. And then you have this kind of corresponding understanding of how you could design it differently. Because if you're going to tab something, you have to design it to work that way, right? And so that has been amazing. You've seen a lot of that. You've also seen a handful of people take shots at trying to innovate around the elements of facilitating manufacturing. So if you think about like what a Hadrian has done, or what FormLogic tried to do, or frankly, what Rapid did, and a lot of Proto Labs, right? A lot of what these companies have done, going back 10 plus years now, around trying to take what is otherwise an individual discrete site where something is manufactured and apply the manufacturing line philosophy to it, right? And to try to automate that. And what's crazy to me, and some really cool stuff, right? I think there are incremental gains you can probably have by having some of those things, right? Some of the things is just being able to run a second shift or third shift, being able to run lights out. But the crazy thing to me is that if you go to actually look at the practical realities of what it takes to facilitate a supply chain, OEMs through the tiers, there are massive gulfs where you see there's just total analog handoff, or just nothing at all being happening, right? Like an actual drawing being sent via email to someone, complete cutoff of communication between them.
Yeah, no, which is totally illogical because there are fundamental, and this comes to like I think the punchline, right? We have an industry where, and we have an industrial supply chain that is fragmented, using different technology, so speaking different languages, which creates data asymmetry and arguably declining fidelity in data as you move through the supply chain.
I don't think
A
anyone
lot of
would argue that point. Go look at what a finishing shop gets, and
oh
who are they
yeah,
going to talk to? They're going to
that
talk to their next customer, who could
yep,
be tears away from the designer of it. Like,
exactly right.
it's
So
crazy.
so we have data asymmetry, we have declining fidelity of the data, of technical data, and then you also then layer in information asymmetry. So we're relying on humans to interpret data into information to make good decisions. That is what's happening in the industrial supply chain, and those humans are retiring. And that is what's, I think that is the single biggest risk to supply chain resiliency in the United States, especially because we just do not have those translate. I mean, the word translation, we don't have the people that can read a PDF drawing and understand exactly what that means for their business.
Yeah, what you've got is you just described, using some other word, you just described basically an information gap and tribal knowledge walking out the door, right? A lot of times it's walking out the door on both sides because it's someone retiring on either end, right? But there's a critical communication gap. And I think you broke it into pieces, right? Like you have the data asymmetry, which is okay, you've got the designer here, you've got the tiers, and the tiers, each of them have like less information. You've got declining fidelity because you have people redacting things or not sending the whole thing. Then you've got your information asymmetry where you may have some people who understand what was trying to be done in
Yeah.
one place.
Well, you see it from the front office to the shop floor. I mean, it's one of the key problems that we solve with paperless parts. I have a estimator who really understands how they're quoting the part with an idea of how that part will be made. A lot of times before we started selling this software, that would get written by hand on the side of a drawing, thrown in a drawer or in the garbage. And when they would win the job, someone else would think about how they were going to make it. And there are millions of different ways to produce the parts. So now you have that problem from the OEM into the supply chain. The OEM has an idea. They are thinking about this. They're like, we're going to put it on this kind of a machine, and then we're going to flip it this way, and this is how we're going to use the tooling, and this should produce X cost. But then when they go out to their supply chain, they don't tell them that at all. They give them a 2D drawing and say, give us your best price. And then they're amazed when the prices don't line up. It's like, they're like, wait a second. Like, why do they think it's so expensive? And it's like, well, did you tell them how to produce it? Then
Or
you like,
manufacturability.
oh
I
my
mean,
gosh.
the number of gotcha features that an OEM knows about and doesn't necessarily have an easy way to send down their supply chain.
And it's crazy because our customers actually believe that this is not a systemic problem from technology. It's not a tech problem. They believe it's just bad acting on the behalf of the OEM. Like the number of times I've heard, they just want us to miss so they can get good on their pricing. And I don't think that's, I really like to take the tilt on the world that people generally are trying to do the right thing. Like I don't think there's that level of malicious, like, oh man, I hope they miss this tolerance and estimating and then catch it when it gets to the shop floor. Like that's asinine.
So I look at it from a motivation perspective, right? So the people, if you just think about who the people are who do these things and what their motivation is, right? So your procurement person or your sourcing person is going to be the person who's actually getting the price, right? Like they're the one who is going to select the manufacturer. And they're typically pretty junior people at these companies, right? A lot of times they're people who are fresh out of school in some sense, maybe grad school, but they don't have a lot of context on all this stuff, right? And so they're just trying to say, okay, what do I reasonably think I can get a yield out of? And that
Yeah.
somebody's going to make the parts that, and I know them, they're on my approved supplier list, right? They they have a history making parts made out of this material, maybe, right? They might have that. They're looking for that. The person who has to deal with it if the supplier screws up is the supply chain person who didn't make the choice
Yeah.
to go with you. And so that person is just stuck. Like that person's entire job is just managing stuff rolling downhill at them,
Yeah.
right? All they're trying to do is just like make it through the day and get out of it with as few exceptions as possible.
And and now you have silos inside of these large OEMs, like any business, right? And each silo has their pet software. So whether you have your CAD and your product lifecycle management systems that are trying to stretch across multiple silos, but then procurement is done in entirely different systems. Whether you're working in Ariba or some other type of a procurement system, it just creates. I mean, we could spend hours talking about how portals came to life and why, everybody's been trying to work around this problem. And I think now the punchline for me, and just as we've gone through this exploration, is never been a better time to create a solution that connects the nodes of the industrial supply chain.
We're going to solve that communication gap.
The 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 technology, the security, it all exists. And I think this industry is so ready for it. I think manufacturing in general, I think the pace of innovation that can be harnessed, we already talked about it. The speed is there, but speed in bits and atoms, in ones and zeros is nothing when you're trying to produce a physical product. You need speed through the industrial supply chain, and you need agility. Like Scott, our co-founder, always says, right? Agile hardware. How do you create agile hardware? And the way you do it is by raising the level of fidelity of information, creating data symmetry, and then creating information symmetry on top of that. And I think that's how we solve this problem.
Well, we're going to try to solve it.
Got nothing else going on. It'd be fun.
Good conversation, Jason. Thank you for the time.
Awesome, Ken. Good stuff.